So today the first lecture we have, so that's a lecture on the introduction to machine learning. And what I want you to say today is the first thing that what is basically a machine learning, what you're gonna study throughout all this course, and well, some basic things about some work of machine learning engineer and what you will do if you will try to create some sort of project in machine learning. So probably I don't need to say you that machine learning is now getting into almost all branches of our life. So here is an example of a Tesla automobile that is so-called self-driving car. So machine learning methods are able of detecting some sort of objects and making this car to drive throughout the street without getting into troubles. So some different machine learning methods are often used to make photos better. So you see an example of photo denoising. Machine learning methods are capable of understanding the 3D picture. So you are seeing a photo. Photo is it's just flat, so just some bunch of pixels, and getting this bunch of pixels, some algorithms, some machine learning algorithms are able to reconstruct and somehow understand the 3D structure of the scene it is seeing. These algorithms are able of creating some sort of realistic images, playing games, and even creating some sort of pictures in style of some artist. So you see here the picture of Kandinsky, and we are transferring this style to some photo of a random cat from the internet, and you see that now we have a Kandinsky cat. Not only art, but science as well. We can use machine learning methods to do something scientific. So for example, in quantum chemistry, we are able to calculate some sort of energies and predict binding energies for molecular orbitals and for different chemical structures. We use machine learning methods in computer-aided drug design. So there are two main branches, so-called direct screening and inverse screening. These are the methods when you are trying to calculate the energy of binding of some sort of chemical compound, some molecule with some selected protein. Or in case of screening, you are taking some sort of some protein you are interested in, and you are searching for molecules that can bind to it. Or inverse, you use a molecule and you are searching for protein that it can bind to. This is a very interesting test for pharmaceutical companies, because if you are searching for some sort of new drugs, you are interested in components that can be biologically active. And your component is biologically active only if it binds to some sort of receptors, for example. And you are really interested in in solving all possible chemical components that you can synthesize to get the ones that have some perspective of becoming biologically active, and then you can test them on something more relevant. I don't know, for example, first on some bacteria, on mouses, and so on. Computational structural biology. Probably you have heard about so-called AlphaFold from Google. So you probably know that at the moment we have some machine learning algorithms that help us to understand structure of the protein. If you are just having some sequence of amino acids, it is composed of. So you are having just sequence, so just primary structure, and you are trying to calculate its secondary, ternary, quaternary structure, so getting some ideas how it will look like, and probably how it looks like will give you some idea what it does. All this information is used in material research. So people are trying to get some ideas of what can we synthesize, so what kind of chemical compound do we need to make so that it has some predefined properties. So we want some properties. We want this material to be durable. We want it to be a really nice conductor, or we are searching even for superconductors and so on. And machine learning methods are helpful in these cases, and they can help us to get some idea where should we search for something. Of course, they cannot substitute the whole procedure of experiment and doing all that sort of physics and physical theories and physical experiments, but at least they can give us some hint. So when we are getting too much possibilities, too much information, they may help us to choose something, so throw away some cases that we consider are not very perspective, and just focus on the ones that we might think they are some sort of perspective, so we can get something out of it. Okay. So probably you know much more about all these methods in real life, because you probably used Google Translate. It uses some sort of neural networks to help translating text. Probably you used so-called Chat GPT from OpenAI. Even I use it sometime and pose it some questions and look what it says. But I think what I should say you right now is basically what is machine learning, and it's quite interesting thing to try to define what is a machine learning program and how does it differ from some sort of traditional programming. So I want to show you at least two points of view on this thing. So the one point of view is a point of view of an engineer. So how engineer might say what is ML program and how is it different from a traditional program. The other point of view is a point of view of a mathematician. So how a mathematician thinks about all these things. So let's make a picture. So suppose let's try starting from an engineering point of view. So I have a program. So what is a traditional program? It's just some sort of algorithm. It gets some input data and it gives you some output data. So nothing fancy. Some input, some output, and the program itself is some sort of predefined number of rules that tell you how do you make from your input, how are you making your output. That's okay. So for example, if you are trying to write a program that will tell you if you are, for example, eligible to get a driver's license. So what you may want to do, you want, for example, to check if you have, I don't know, 18 years, for example. So your program will be very simple. So you are checking something like if age greater or equal 18, you are saying yes, so okay. So you can have. Else you are saying no, it's too early. Okay. What about ML program? How would it differ from this thing? So you will have a program, once again, that will take some input data, but in this program you will have some sort of free parameters. Some sort of parameters, I don't know, let's call them new, x, whatever. So you are having these parameters. This program works only when it knows the values of these parameters. Where does it get these values? There is some separate algorithm in here that will set these values of these parameters. This algorithm is taking as an input some database. It takes some data. This is the training algorithm. So this program won't work before you define all these parameters. You define these parameters by so-called learning or training your algorithm. You train you are training with some sort of separate training algorithm that uses some data to get insights into these parameters and set them somehow. Only then this program starts to work. This is ML approach. How does it look like in this case? So for example, I want once again, I want some program that will say you if you are eligible for getting some sort of driver's license. Okay, so this program will look like something like this. So if age is greater or equal some parameter, let's call it a, then you are telling okay, else you are saying no, no, no. You might see that if I don't know what is the value of a, this program just can't work. So you need some separate algorithm that will set this value of a, some predefined numbers, I don't know, 18, 16, whatever. How do I do that? I will have some separate algorithm like this one that will train and will get me this a. How can it train? For example, I will say, okay, I have a database of all issued driver's licenses, that all the licenses we have. I can look through that database, look through the ages of people that have received the driver's licenses and find, for example, the minimal age. That will be my training. So, for example, this one will take some sort of minimal, let's call it min age of some database of issued licenses. Then this value will be set in here. And then this program will start to work. This is ML approach. So we had some parameters and we trained them. So we found some different algorithm that was able to define these parameters for us, and then it started to work. Okay, it looks a little bit convoluted, but probably, as I always say to my students, there are no solutions that are absolutely good or absolutely bad. So there are always some pluses and some minuses to any solution. And what I want you to think right now, so just for a moment, what are the pluses and minuses of these two solutions? Why do I may want to write a traditional program, and why do I may want to write a ML program? How do you think? Yes, please.
The first case is totally predictable and we know how it works and we can make any changes we want.
Okay, so this is the plus. So it's much simpler, for example, yeah, it's perfectly predictable, so what we coded, that we see. Okay, what about pluses of this case?
It can solve tasks that we cannot solve with the first approach. Or if we use the first approach, it will be too difficult. Like to write the exact program that would predict things we are interested in.
It's very similar to the first program, but I want you to think about a little bit different case. So, for example, suppose we are in United States, and different states, they may have different ages to make you eligible to get driver's license. What do you do if you are going from one state to another to make this program work? So, for example, you are getting to some state that you are able to get that license at, let's say, 16 years or 14 years. What would you do with this program?
Modify it.
Yes, you should rewrite it. You should rewrite it and to get a new program. What do you do in this case?
You can just only change the data and it would relearn again.
Yes, you take different data and you just rerun it. So here you rewrite it, here you just rerun it. So this is a big plus. This approach is adaptable, so it is able to adapt to some new data that you are getting in. If anything changes in the environment, you can just rerun the program on your new data, it will relearn, get some new constants, do something new, and then you are able to use it once again. So no need to modify any code. With this program, yes, it's much simpler, but you will need to modify this data every time that something changes in the environment. So you are getting to a different state, you need to change this constant, and so on and so forth. Of course, it is a very simple example, and if you will get into some much more complicated things, you will see that this gap, this difference is getting much and much bigger. And in many cases, you would like to have some programs that you don't need to modify. You can just take them, you can just rerun them, change something in your data and get something like a brand new program that works in a very different way. So for example, if this is some sort of neural network, you can train it to recognize cats. If I want it to recognize dogs, I don't rewrite the program. I'm not changing all sorts of ifs, fors, and so on. I'm just taking a different database with, let's say, with dogs. I'm loading into that program. I'm telling it, train. It trains and it starts recognizing dogs. If I want it to recognize something different, so I don't know, some computers, some sort of trees, whatever, I'm just getting a new database and I'm just retraining it, just rerunning. No changes in code, and this is really good. Okay, this is an engineering approach. So we are looking at it like engineers. So we are doing some program, we are setting some parameters, so on. There's a different way to think about all these things. It comes from a point of view of a mathematician. So let's... Okay.
You can just turn it, yes.
That's why I don't like whiteboards. Classical boards forever. Okay, so a mathematician's point of view on everything. So what we are basically doing, we can think about every our program as some sort of function, some function that gets some inputs and it produces for you some sort of outputs. What we are basically doing when we are training our algorithm, we are searching some function that will suit to our needs. So we need some function that gets as an input, I don't know, some image, and produces you whatever on this image, for example, is a cat. So it just creates for you some true or false. Looks very simple. But how do we find this sort of function? We know that there are many functions. So, for example, as the mathematician, you will know that there is not just infinitely, but uncountably many functions. So you just can't take every one of them and check if it suits to your needs, if it does what you want it to do. So what are we doing in these cases? So in these cases, we are taking some subset of all the functions possible. So we are taking just some subset, and we are searching our function we need in that subset. So for example, here are all the possible functions in the world. Here is the perfect function that can map you every image you are taking in into some true or false, and perfectly defines whether there is a cat in that image. So it takes you some sort of input and produces you output. And these are all possible functions in the world. Of course, I can't get through all of them. So what I'm doing, in some sense, I'm taking some subset of this function, of all the functions, and I will work with this subset. The perfect function I'm searching for may be in this subset, or maybe not. That depends. But in any case, I should take some subset just because that's physically impossible to get through all the functions. So that's what I do. How do I do that? Let's create some connection with engineering. How do I do that? Depending on the machine learning method, I will show you that methods when we will get through the semester, but probably you heard of some of them. So for example, you heard about neural networks. And you probably know that there are some sort of layers in that neural networks, and you are setting some types of these layers, and you are creating so-called architecture of the neural network. What you are basically doing when creating this architecture, you are creating some set of these functions. Why set of functions? Why not one function? Because before you have defined every parameter on that layer, for example, before you set it to be this one equal to 1, that one equal to 10, that one equal to -5, and so on. Before that, you are basically dealing with all possible functions that you can define when setting that different parameters. So this can be a set of something. Let's take something very simple. Let's take I don't know, linear functions, kx plus b. So let these be my set of functions. So I can define that in code somehow. These are the free parameters I told you before when we were talking about engineering point of view. So these are free parameters. And this is that of all my functions. Now what I'm doing, what is training in this setup? It's searching for the function that is the closest one to the perfect function. So I'm searching through this set. I navigate it with the help of these two free parameters. I can index all this set, and I'm searching in this set for the best function. I find it, and that's basically that completes the training of whatever algorithm I work with. So this is the thing. So as mathematicians, we are basically searching for such a function from some subset we have defined on our own. That depends on the method we use, that depends on some sort of restrictions we pose on our problem. And we are searching in here for the function that is the closest one to this one, to the perfect function. That's what we do. Okay. Now let's get further. I have a message in chat that they have problems with board. Okay.
I shared the photos with them, just the photos of the board. But for the next time, we will fix it.
Okay, that's great. Okay, let's get quickly through all the rest things I wanted you to say. First of all, so fundamentally, what is machine learning? It's basically about building mathematical models that help us to understand data. So basically, it's building models. So that is the essence of the machine learning. Even if you are creating some neural network, you might not think about it like building a model, but basically, yes, you are creating a model. So you are defining all that set of possible functions just by setting all the layers that you will work with, and then you are training it. You are basically searching for the function. What is learning? Learning in this context is basically giving this model some tunable parameters that can be adapted to the observed data. So you will take the observed data and you will somehow find these parameters. How would you find it? Depends on the machine learning method we will talk about. Data is always represented as a collection of data points. So if you have a data set, that's a collection of data points. Why data points? It's a sort of method to underline that these are some points living in a multi-dimensional space. What are these dimensions? So each dimension you have in your data point is called a feature. So what is a feature? Feature is a measurable property or a characteristic of a phenomenon being observed. So if you are taking an image, your photo camera is basically measuring how much photons, how much light does it get at some point in space. So that's basically a measurable characteristic. You can use it as a feature. You can, of course, generate some features on your own. So you can take some input and you can somehow calculate some new features from that. That's pretty okay, and moreover, all the classical machine learning methods, they are basing on the fact that you will create some suitable features on your own. So basing on the understanding of the problem you are investigating and so on, you will create that features. Okay, so machine learning is good, as I told you. So it's good for problem when you are getting too much rules, or list of the rules to get solution is getting too complicated or too convoluted. So machine learning code can simplify that in some way. you can use it for fluctuating environments. So if something is changing in the environment, your machine learning system will be able to adapt to that new environment, and that's really good. And you can use machine learning methods to get some insights into data you have. So you are having a large amount of data, and there are some machine learning methods. So for example, reduction of dimensionality. When you are able to squeeze your data, you are having some sort of, I don't know, 100 dimensional points somewhere, and you can't even imagine what are they, because our imagination is stuck on 3 dimensions, so we can't get beyond that. 3 dimensions, and that's all. But we can, with our machine learning methods, we can create some sort of picture of what will happen if we squeeze all that data into, for example, 2 or 3 dimensions. And it can get us some insights into that data. We will see there are some sort of, maybe some sort of clusterization, maybe something else will happen. We will see that. Okay, so types of machine learning algorithms. There are many kinds of classifications of machine learning algorithms, but I want to show you just one that is often used. So I just wanted to know the terminology, so nothing more. So first of all, supervised learning. That's when you are modeling the relationship between measured features of data and some label associated with that data. So you are basically as an input for your training algorithm. So when you are training your algorithm, you are given it as an input, some input data, and the output you want it to produce. So that's basically supervised learning. So you say, when you get this input, I want you to create this output, and so on. And you have the whole data set of such inputs and outputs. Many methods fall in this class. It gets in future into 2 branches. We will see that's classifications when labels are discrete categories. For example, if you are putting some photos in and you wanted to find, for example, these are photos of cats, these are photos of dogs, and so on. And regression, when labels are continuous quantities. Probably you have seen linear regression, and this is the perfect example. There are many other examples of supervised learning. I know, k-nearest neighbors, linear regression, logistic regression, support vector machines, decision trees, some neural networks, so on. Unsupervised learning is basically when you are modeling these relationships without giving any label to your training algorithm. To get some better insight, I just show you an example of such algorithm, just one of them. Let's say these are my data points. Coordinates, as you might guess, that's features. So this is some sort of feature 1. This is feature 2. And one of the examples of unsupervised learning may be clusterization. So when you are giving these points to your machine learning algorithm, it takes them in, it produces two clusters. It tells you that these points are in cluster 1, these are in cluster 2. And then it's able to divide all the plane into 2 parts and say that these points are closer to this cluster and these points are closer to that cluster. So in some sense you haven't given any label to the algorithm. You may not even tell him how many clusters there are. But it finds these clusters and then it's able to classify some new points that are coming in based on the previous data. So that's some sort of example of unsupervised learning. There are many other methods, so like dimensionality reduction I have mentioned before. That's methods like PCA, LLE, TSME, and so on. Okay, and reinforcement learning. So I just wanted to show some nice picture of the reinforcement learning. It's based on the idea that you can create a program that interacts with the environment. Environment changes, influences it somehow, well, something happens. And it can estimate the result of what happened. Is it good, is it bad, whatever. Then return to the starting point, but it has some new information. It has some new information. If I do that, that would happen. And it can train on that information and maybe make some other choices. So for example, we have some environment, we have an agent in that environment, and that agent does something. It has no information on the environment, so basically it's a random choice to go left or to go right. But when it goes left, it gets some sort of, say, damage. And now when our agent returns to the starting point, it has some new information on the environment. It knows that going to the left is not very good. And it can train on this new data and then make some different choices. Probably you have seen some sort of videos on the YouTube when some tiny cars are driving through some convoluted road and they are training all the time. So it's some sort of reinforcement learning. So they are always, I don't know, getting into some troubles, and all the time they are retrained, and at some point they are able to get through all the very long and convoluted roads, through all the track from start to finish. Looks very interesting. One simple example of what can be a problem and why it can be quite complicated for us and for a computer. So the simplest example, you must think of everything I told you before, in the classification problem for two classes. So just two classes. It's called binary classification. And you might think it's a very simple problem. We are just telling true or false. But what I always show is the problem. I show you right now a bunch of pictures, and I want you to think, is it complicated or not to classify them? There are just two classes, dogs and muffins. And probably you might see that there is a bit of a problem. So even a binary classification may be quite complicated task to perform. Okay. Now, how does the work of the machine learning engineer look like? Let's make some sort of 10,000-foot view. So first of all, you are getting some problem. And where you want to start is you want to study the problem. You want to look at the big picture. You want basically to answer the question, do you need machine learning in this problem? Because there are many cases when you have a problem that basically doesn't need any ML. And using it there would be not a very nice idea. So for example, if you need for some project, you need to get the idea where some photo was done. You may employ machine learning, you may search for different photos on the internet, compare this one with all the rest photos and try to get some basic idea that this is a photo, for example, of Eiffel Tower or whatever. But the problem is that maybe for your project would be enough to check the metadata of that photo. It often contains some sort of coordinates that will tell you, some GPS coordinates that will tell you where this photo was taken. And probably you don't need any convoluted, any complicated machine learning methods. So the first question you should answer, do I need machine learning in here, in my problem? If it looks like yes, I need, so your problem is falls into some of the categories that I told you. So you are having some fluctuating environment. You need your program to adapt all the time, or it looks like that traditional methods will be too long or too complicated to solve it. Okay, so you are getting into ML. Now, you should think about what data can you get. Basically, what I'm always telling, that getting a good database, getting a good data is approximately, I don't know, 80% of your success. You can take some sort of not very good model. You can take some wrong architecture of your neural network. You can do some other things, and it will work somehow. It will work even not bad. But if your data is bad, if you can't get data of enough quality, if you can't get enough data, that's a disaster. So it's not worth doing. If you are seeing that no data is available, you just can't do anything. It's no reason to start even doing something. Because you need, first of all, you need data. Of course, you need to consider all the problems you might have with that data, because often you can get the data incomplete. It may be complicated to get some data. There may be some legal issues with getting some data, so maybe you are just not allowed to have that data. And these are all the things you should think about when you are basically studying your problem. So how do you get some data of high quality and enough data? The second thing, of course, you can try, if you have some data, you can try to visualize it, you can try to get some insights into that data, so maybe that will tell you something about the problem, and you'll be able to solve it some more efficiently and so on. Only then you are thinking about selecting and training the model. So if you already have some data set, and now you can think about your model. Of course, if you know your problem, you basically will know the class of the models you should search within. So if that's a classification problem, you can search among some neural networks, try a support vector machine or some trees and so on. If you are doing regression, of course, you might think about some sort of linear regression or some more complicated methods, so whatever. So you are basically training your model. You are choosing so-called hyperparameters. So some models may have some parameters that are not trained, but that are set by you from the external, and they are called hyperparameters. Well, there are many different hyperparameters you might think about. It's I don't know, like learning rate, for example, or something else. Number of clusters. So number of clusters may be thought as hyperparameters. So if you are using some kind of algorithm that is basically that is based on the fact that you have some predefined number of clusters, so that number will be a hyperparameter to that algorithm, and so on. Now you train your model, you can use it to predict new data and so on. But that's not all. So just training the model on the data, so you got data, you trained your model, it looks like, oh yeah, I'm finished. No, you are just at the start. It's just the beginning. Why? Because first of all, you need to evaluate your solution. And the evaluation of your solution is much more complicated than one might think. Because into that evaluation, you are basically incorporating what you are thinking to be a good solution and what you are thinking to be a bad solution. And I will show you, just in a moment, I will show you that this is quite a non-trivial problem. And you should think about so-called business metrics and so on to get your evaluation right. So that's really some sort of, I say even some sort of art. So you should create some evaluation method that will basically, that into it you will incorporate all your ideas of what is good solution, what is bad solution, and these ideas are defined based on the problem and what you want to get from it. And only then, if you did all that evaluation, if you see that everything is okay, so everything works great, maybe you change the model if it performs poorly. Maybe you get some more data, whatever you do. At some point you say, now results are good enough. So now evaluation tells me that results are okay. Only then you can launch your solution, you can present it, you can, I don't know, start some sort of startup maybe. Okay, so where are humans in all this scheme? Just to reiterate. So computer, it's like one more pair of hands for us, but it can't substitute us for, at least for now, in some sort of thinking and some ideas. So there's always some place where a human should intervene and change something in that pipeline. So you can't just get some bunch of data to a computer and say, make me a model that will do something with that. So it's not how it works. So first of all, of course, you are choosing the model. So you are the one who chooses the model and say, I want neural network here, I want support vector machine here, I want something else here. Second thing, imputation of missing data. You are the one who says, what do you do if you are missing some data? So your data set may be some sort of big table, and some parts of this table may be missing. And you are the one who will tell, if some data is missing, for example, I throw away the whole row, or I throw away that column, or I use this data, but I will use some, I don't know, some dummy variable into that data. So let's say I will put all missing data to 0, or to -infinity, or whatever. That is the choice you make, basing on the model you will use, and basing on some ideas on how good will it work, or how bad will it work. So that depends. Feature engineering. You may create some new features for your models. So maybe you are thinking that that input you have, I don't know, for some reason your models work poorly on that input. But you might think, well, maybe if I take all the data that I'm using as an input and I find some, I don't know, something squared, I don't know, something adds, minus, so on, I will create some new numbers. That will be my new features. And my model will work better on that features. That may be. Of course, it's a human work. Why? Because you are engineering these features basing on the problem. So on your understanding on the problem of what you are doing. So does it make any sense even to calculate the features? So if you are studying some physical system, you may calculate, for example, I don't know, kinetic energy and use it as a feature. That makes sense. And you can engineer that, so take all that velocities, square them, so on and so on, and you calculate kinetic energy, and that's okay. But machine doesn't know what is kinetic energy. It won't engineer this feature for you. And of course, we are much more aware of some problems that's like lurking variable or some other such things. So only a human right now can understand if you are getting some result from the machine, how meaningful is it. As I want to show you just an example to get some taste of what I mean by that. So for example, you are doing some research and you are trying to estimate whether some data, some time series are connected with each other. So probably you can just load them into machine and tell them, well, take all this series and search me for something similar. So if you see that some points are quite similar, so there is a huge correlation quotient, for example, you see that plots almost overlap and so on, tell me that these plots are very similar, so probably there is some connection between the thing that plots describe, between the time series. And here is the example for you. So you see two plots. They are quite similar, as you might see. They have some stunning correlation quotient, like 99% or something like that. So it looks like these are some connected processes. So something happens, it grows, the other thing grows as well, and if it goes down, the other thing goes down, and so on. So they look quite similar. So you might expect that machine will tell you these processes are connected, so maybe one is the reason for another. Why not? But if you look what is this data, you will see that this is basically the amount of money that the United States is spending on science, space, and technology, and the number of suicides by hanging, strangulation, and suffocation. So if just, I don't know, maybe if American scientists get so much money and they get so happy about it that they go and hang themselves, I don't know why should these things be correlated so good. So probably machine will tell you that that is a good correlation, that there is some connection between the things. But only a human can look on it and tell, no, it has no sense. So it just happened. It's just a random thing. It just happened that these points are aligning so good. But they can't have anything in common. Okay. And of course, the example with so-called lurking variable. So probably you know that there will be some sort of correlation between, I don't know, number of people that drown and the amount of ice cream eaten. But probably eating ice cream is not the reason to go drown yourself or the other way around. But there is a lurking variable in that. So there is some common reason that makes you consume more ice cream and makes, let's say, bigger probability for you to drown. How do you think, what is this lurking variable? What's the reason behind these two things?
Summer.
Yes, correct. It's summer. In summer you eat more ice cream because it's hot, and of course in summer you go to bath. So probably if you don't bath, there is no probability of being drowned. So of course summer is the common reason. But if you just draw some plots, you calculate some correlations, you will find that there is something between these two parameters, but only a human can tell you, no, there is no direct connection between ice cream and being drowned. But there is some sort of common reason. Okay, now the part about checking your model. So as I told you, if you have already created your model, so you have studied your data, you have chosen some model, you have trained it, okay. Now what we want to know, how good is your model? So you train something, it somehow works, it produces some results, but maybe these results are some sort of garbage, so maybe you can't do that. Or maybe they are perfect, so how do you check that? Basically it's not so simple. It's not so simple, first of all. The second, there are some common mistakes that people make when validating their models. So it's called the process of validation. And the first thing I want to show you, it's a very big warning. I want you to know it from the first lecture, so if you will do some of your models, I want you to know about it already. So never ever validate your model on a training set. So you should have separate set for validation and separate set for training. So never validate your model on training set. There's a really nice tweet I have even posted here. So data science fact. You cannot validate a model by showing that it predicts its own predictions. Sounds obvious, but people routinely do. And that's really the case. If you are validating your model on your training set, you are basically validating that it predicts its own predictions. It doesn't make any sense, so don't do that. You need a separate set. Okay then, you need separate set, and how do you get it? Of course, quite natural question you should pose me, so how do I get that set? There are many methods to create that set. So you are basically, what are you starting with? With a large data set, so you have a bunch of data. Now what you do, you are basically splitting that set into parts. And one part you will use for training, the other part you will use for validation. How do you do that splitting? There are many methods. I'll show you a few that I want you to know about. So first of all, the simplest thing, hold set. In many cases, we just take the whole data set. We take, let's say, in most cases, 25% we set aside and say it's for validation, and the other 75% we use for training. So very simple method. So just splitting it into two parts. It's easy, it's time efficient, it's used for big shuffled data set, it's really good. It has one minus. Unlucky splitting may cause some problems. So if your data set is not well mixed, it may happen so that you are having your data set, let's say, okay, maybe I'll be able. Okay, so let's suppose this is my data set, and if it's not shuffled good enough, it may happen that I have, for example, 4 classes in there. I don't know, some cats, dogs, trees, whatever. And if I am unlucky enough, it may happen that I will split it into training and validations, something like this. So as you see that there are no objects of these 3 classes in my validation set, and almost all objects of this class are in my validation set, but almost none in training set. That's very bad. Of course, you can't expect this sort of splitting to work, because you are basically testing your model on some sort of data points it have never seen. So it's really no good. Of course, we should do something about it. And to do something about it, we have some different methods. For example, n-fold cross-validation. Really nice procedure. So it solves, at least to some degree, the problem of unlucky splitting. Here, well, basically, I will first show you how it works, then maybe I'll pose you a few questions just to think. So, how it works. First, I just split my set as previously. Let's say 75% for training, 25% for validation. I perform validation. Then, I'll do the next step. I will take the other 25%, as shown in this picture, for validation, and the other 75% for training. Now I do this thing once again and once again. So with that part of validation, I have stepped through all the data set I had. Let's say 4 times. Of course, you can do that 5 times. For example, take 20% for validation and 80% for training. You can do that with 10%, so whatever, that depends. And here I got basically 4 numbers. So each time I have validated my model, and I have somehow predicted how good is it. I see there is the question. Yes, please.
Okay. About training and test. I sometimes read about 3 types. Let's see that 3-part data. It's training, test, and validation. Training we have 70% test, 20%, and validation 10%. It's for better result and understand how it works, our model. What do you think about it? It's normal, but it's enough have 2-part data.
Okay, I think I understand what you mean. That basically depends on what are you doing. So for example, if I have just one model, and if I'm getting I just want to get some idea how good is this model, it's okay to split into 2 parts, train and validation. But it may happen that you have in your model some sort of hyperparameters. And you just you don't want just to take one set of hyperparameters, but you want to try different sets of hyperparameters. And in this case, for example, you might want to use splitting into 3 parts. So you are training your model, you are validating it with some hyperparameters, then you are taking that model with different set of hyperparameters, once again validating, so on and so on. You are getting a bunch of validated models, and then you take, let's say, the champion, so the best model, and you test it once again against the data it hasn't seen, so against that third part that you have separated. So that may be the case. It's often used if you are comparing some different models. So if you have 2 or 3 different competing models, you want to test the winner against some data it hasn't seen. Why? Because you want to know its quality. So you want to know its basically its quality, and to get that quality you are performing your final tests against data it hasn't seen. So that may be the reason for splitting into 3 parts. Yes. Okay, one interesting thing I want to ask you about this sort of splitting. So, yes, please.
I'd like to ask, by talking about cross-validation procedure, you don't mean splitting in time spent for training and validation. You mean 75 to 25 split between the pictures used to train and the pictures used to validate?
If pictures are your input data, so you have, for example, some neural network that takes it as input, and you are having a data set, for example, I don't know, 100 pictures, a small data set. So basically this splitting means that I take 25 pictures and I put them into folders that I call validate, and the other 75 I put into folder that is called train. And I use that folder train to train my model. I don't show it any of the pictures from validate. Then, when it's trained, I take that 25 pictures from validate, I put it into model, and I look how good it performs. So, for example, they were labeled somehow in my data set and so on. And this is the first step, as you see here. So the first trial I did. Then I take once again the same data set, but I put different 25 pictures into the folder validate, and the rest 75 into folder train. And once again I retrain my model from scratch. So I throw away everything I had before, and I retrain it from scratch on new pictures, and once again I test it on the validation set, on that new validation set. And so I do 4 times, and I get 4 different numbers. And here is an interesting question for you. This procedure, besides getting me some idea what is the quality of my model, it gets me some new piece of information I couldn't have before with the previous methods I showed you. How do you think, what is this piece of information?
The level of the data, how much is it homogeneous, like, or whether...
No, it gives me some piece of information about my model. What else do I want to know, except it's like quality I get on some
is
set.
it like robust for different...
How general the model is, maybe? Like, how does it perform on a different data? It is quite similar, but is different in the end.
Well, basically the whole validation procedure, by any way I do that, it's basically targets the idea to check the generalization, to check how good it performs on the data it haven't seen. But particularly this one, n-fold cross-validation, gives me some new piece of information about the model. And there was a good term, so robustness of the model. So if something changes in your data set, you don't want your model to change drastically. That's a bad model. So you want your model to be, in some sense, you want it to be stable. So if I'm throwing away some pictures from the data set, I'm adding some new, I'm doing something like that. From the good model, I would expect it to still perform on the same level of quality it did before. So these changes should not, I don't know, like break the model or make it some perfect. It's no good. That's a sign that your model is unstable. And if anything, some minor things changes, it will just break down. It's no good. And when you are performing all these retrainings and validations, as you might see, you are having, every time you are having a slightly different training set. So you are retraining it on a little bit different data. So probably you might expect, if your model is very unstable, it may break down there somewhere. And you will get the idea that something is wrong with your model. So maybe you need to use some different model. So the stability of this model, the robustness of this model to some small changes in data set is the new piece of information we get from this sort of cross-validation. And it's really good to know. Because probably if we talk about all that cases I told you before, so the big plus of machine learning is the adaptability of all that programs to the changing environment. So you are getting from one state to another, you don't rewrite all your codes to get all that information about, let's say, eligibility for driver's license. You just rerun it on new data. And of course you want your model to be so good that if something changes, you just rerun it and get new results. If it doesn't work that way, so probably it's not a good model, so maybe you need to check for some other. Okay, here is an example of cross-validation in case of ducks and muffins. I don't want to stop on it for long, just basically the same picture. Okay. So-called stratified cross-validation. Once again, if your dataset is not mixed good enough, you still may get into troubles with all that cross-validation stuff. So if you are really unlucky, so here is one of the examples. So you say you have 4 classes in your dataset. It somehow happens that they just go one by another, and if you are splitting your dataset into chunks, so you may get into the situation when one class gets into validation and the others will go into training. Of course, it's a very extreme case, very rare, and you're not probably gonna face that, but it's a reason to think about maybe we can do better. And we can do better. We can do so-called stratified cross-validation procedure. So when we, let's say consciously, we check how many of each class there are representatives in the data set, and we are choosing into validation and into training set basing on that information. So here you see, once again, I'm taking some data into validation, some data into training. Once again, it's 25 and 75%. But this time, I have checked every class in my data set, and I'm consciously checking 25% of each class into my validation set and 75% into training set. And you see how that goes when we do trial 1, trial 2, trial 3, and 4. So once again, everything I told you about cross-validation, that applies, but here you have one problem less, just because you will always get your classes in your training and validation sets. Shuffle split cross-validation procedure. So you are basically taking some random points from your data set and putting them into validation and training set. You can left some points unused, that's okay. Here is once again the example. So some points were taken to train, some points were taken to validation, and once again we did a few trials. There's one interesting plus to this procedure when you are doing all that shuffle split. Of course, you are not getting into trouble with all that classes just because you are taking randomly. It's highly probable that you will get let's say concentration of your classes in your training and validation set of the same, so that's okay. There is one more big plus. How do you think which one it is compared to cross-validation I showed you before. Be it simple cross-validation.
Probably.
Yes, yes.
Probably less time for training. I don't know.
Okay.
Smaller sets.
Let me make you a hint, small hint. So for example, I was taking 25% of data into validation. How much trials do I have to do in this case? So I want 25% in my validations. In simple cross-validation procedure I showed you before, how many trials do I do?
4.
Yes.
4.
If I wanted to take 20%, I would need to make
5 trials.
5. Okay. And in here, in shuffle split cross-validation, if I'm taking 25% or 20% into validation set, what about number of trials?
I think it's more. You could say no, it's more trials because it's changing each time validation and training set.
It can be any.
10%.
It can be any number, yeah? I have just decoupled these parameters. I have just decoupled them. So when I'm doing cross-validation, just simple cross-validation, I want to get through all the data set with that validation thing. And I need to do the number of trials that is basically dependent on the size of my validation set. If I'm doing all that shuffled split cross-validation procedure, that's pretty okay. I can do any number of trials, that would be okay. These parameters are decoupled. This is of course a plus, because sometimes I want to make small validation set, but I don't want to do that validation, for example, for 100 times. So maybe that's the case. One more interesting example, so-called group k-fold validation procedure. I want to show you some sort of concept of groups, how it differs from classes, because our models, they basically generate classes. They don't know anything about groups. Groups is just for us. And maybe you will get a little bit more feeling why is it the problem to create a good validation procedure to find some good measurement of how good is the result. So what we want from our model. So I already heard a really correct answer that we want some sort of generalization. So I want my model to work correctly on the data it hasn't seen before. Why? Because, of course, I cannot take all the data in the world into my data set. It's not possible. So probably in the real-life situation, my models will work on the data that I haven't had in my data set. So I have no chance to make photos of all the cats in the world. So if I'm doing some cat detector, I probably should think that it will work on some images it hasn't seen before, and so on. So I need that my program works on any image I put into it. So that's the main problem, let's say. And here is an example for you. So here is a data set. This is the data set for, let's say, emotion classification. So you are classifying whether the person is smiling or, I don't know, frowning. So whatever. 2 classes. And you see here that there are a number of people, so let's say some Barack Obama, Donald Trump, and so on. And I put different people into different groups. So each group is one person. So one group for Barack Obama, one group for Donald Trump, and so on and so forth. Okay. In each of these groups, it has some number of images. Some of them go to class 1, others go to class 2. That's okay. Now let's think about the problem this way. So I am training a model. So I'm training a model. and I want it to generalize properly. And I'm thinking about all these groups and classes, and here is the question I want you to ponder on. So is it preferable to get into my training set and my validation set at least a few photos for each class and each group, or is it preferably to keep some group or groups separately for validation and the other separately for training? How do you think?
Probably it depends on the task.
Let's say in the context of this problem, of this concrete problem. So you are having a data set of photos, a large number of photos. There are different people in that data set. You know about them whether they smile or not. It's supervised learning, yeah, so recalling the term supervised learning. And you can tell who is this. Machine doesn't know, so this data does not go to your model, but you know somehow who is this, and you are sorting these photos into two folders, train and validation. And now is the question, how would you sort these photos? Of course, you would want that you have photos of class 1 and class 2 in validation and in training set. That's perfectly okay, so that's we understand. What about groups? Yes, please.
I would say that we should leave a few groups specifically for validation, because those groups are different from others in significant ways. So
yes, that's perfectly correct.
For generalizability.
Yes.
So, and if we don't have groups that are specific, that are present only in validation set, there is no way to check like whether the model generalizes.
Yes, absolutely correct. So what we want to know about our model, whether it generalizes correctly. What does it mean in this context? So I want it to detect whether the person is smiling independent on that person. So it's really beneficial to put some groups into validation set and don't show it to the model on the training step. Why? Because it can take some, I don't know, some personal features of that people, remember them, and use them when detecting smiling or not. I don't want it to get into that specific features or specific humans that I show to it. I want it to generalize. I want it to work with any human. So whatever. If I show it a photo, I want some result. I don't want it to detect whether Donald Trump is smiling. I want it to detect whether any human is smiling. So for better generalization, I want to test. I am basically trying to get some groups separately into validation set, and that will, in some sense, well, not like 100%, but it will ensure that the model generalizes properly and that it does not work with some personal features of some concrete individual, but it works with some generalized human. Okay. So, yes, we have a question, please.
Can we say that, yes, we have put some groups in the validation set that the model hasn't seen before, and can we say that after the validation process is over, we can look at which cases did the model guessed wrong, and from that we can just see whether the model was wrong on those new groups that she hasn't seen before, or whether it even hasn't trained good enough, so she is not recognizing the pictures of the people she has seen before, and also use this information to in the future development of a model.
Thank you.
Just make it better.
Well, in most cases, when you are performing, well, that basically depends on the model. But when you are training, for example, some neural network, you will more or less assess how it performs on your training set just during the procedure. because you are looking on all that parameters, and how your error drops down. So you will basically get the idea. I mean that you can take into your validation set only some separate groups it hasn't ever seen, and that will be okay. So you don't need even some non-zero overlap between validation and training set. You can just take new groups and that will be okay. In any case, we are interested in whether it works on any person. If it does not work on new persons, that's no good.
Yeah, that's the point of the question. So we can see that, because for example, the model didn't work on these new persons that it hasn't seen before. So it is like it's overtraining, and we need to do something about it. It's not generalizing good.
Yeah, it's not generalizing good. Yeah, that's absolutely correct. So if we see that new faces did not pass, so it didn't work well on them, it means that no generalization was performed by the model. So this model is bad, we need to change something in that model.
Thanks.
Okay, how much time do we have?
About 40 minutes,
Good.
maybe a bit more. But we didn't make a break and we started later, so 40-50 minutes. And if you want a break now...
No, I think we'll okay to get to the end. Okay, so a little bit about metrics. So the first problem. So creating some metrics to measure how good is your model. So that was the step number 3 or 4 I told you before. So you have already created your model. So you trained it. So okay, but now you need somehow to measure how good is this model. So you get some number that will tell you that when this number is close, for example, to 1, it's perfect. If it's close to 0, it's very bad model. How do you do that? And the problem is that, first of all, that depends on the type of the problem. So depending on the type of the problem, like is it classification, is it regression, is it clusterization, is it whatever it is, you will create different metrics. The second thing, there is no silver bullet. And your choice of metrics is basically as valuable as your choice of the model. Because you don't need just to find the correct model. You need to measure its performance correctly. If you don't measure its performance correctly, you can't train it you can train it in some cases. For example, for neural networks, you are writing some sort of loss function, and if you don't write that loss functions good enough for your problem, you wouldn't get the result you expect. So you need to find a good metric for your problem. And what I always tell that you should always keep the end goal in your mind. So there is some sort of thing like business metric, and you should keep it in mind to check against it whether your methods of measurement of the quality of your model, whether they are good or they are not very good. Here's an example for you. Simplest case, binary classifier. So we have some model, it takes some input data, whatever it takes, and it produces to you 2 possible outputs, like true and false. So what do they mean? Basically depends on the situation. And I want you to consider this small table. So basically this table, it contains all possible information you can get about your model when you are putting some inputs into it. So I'm testing my model. So there are some inputs I consider they should lead to true. If the model works correctly, they should be true. I'm putting them into model and I'm looking what happens. If model produces true, I'm doing like +1 into this cell of the table. It's called true positive. So I'm doing +1, +1, +1 anytime when I'm expecting true and my model gives me true. If it produces false, in case I'm expecting true, I'm doing +1 in this cell. So these are called false negative. Very similar, if I'm expecting false and my model predicts me false, I'm doing plus into this cell of the table and it's called true negative. If it produces true when I'm expecting false, of course, +1 gets into this cell, to false positive. And at the end of the day, I have just small table 2 by 2 with 4 numbers, and these 4 numbers, they fully characterize me how good my model performed on the given data set. So that's okay. Looks like quite simple. But the problem is the following. From these 4 numbers, you should somehow construct basically one number. So you should tell how good is your model. Why? Because you want to make comparison with, for example, with different models. You are looking for some good model, you are performing some research, and you should somehow compare them. Moreover, you want to know whether you can use your model in practice. So you want to put it in practice, where basically the rubber touches the road. So you want to do something with that. But you want to know how good is your model. Will it perform well enough to make something from it? And here is basically the problem. How do you get this information from this table? Of course, in case of perfect model, you will expect some sort of diagonal table. Yeah, so everything is true positive, everything is false positive. But well, we are living in a real world, so that's not the case you should expect. Of course, you will get sometimes some false negatives and some false positives because it's a real world. And we need somehow to estimate how bad are they. So how bad is to get 1 false negative? How bad is to get 10 false negatives? How bad is to get false positive? And here is some sort of example for you that shows that depending on the problem, your views may change, so you may consider them harmful in a different way. For example, you are writing a program that detects, let's say, some cancer. So you are putting some information about the patient into your into computer, and it tells you this patient has cancer, or this patient does not have any cancer. And basically, basing on this result, well, that depends whether that person will go and consult with some doctor or not. And in this case, what would you think will be more harmful? Some false negative or false positive?
False negative.
So yeah, so probably not detecting cancer where it is, it's much more harmful than detecting it where it is not. In the second case, the patient will just go to the doctors and they will look at the patient and tell him, well, you have no cancer, it's just some software problem. So nothing bad happened. But if you tell the patient that it has no cancer, it happily goes away and dies from cancer because you didn't detect it. So of course, this case is much more harmful. But there may be the other problem. So you are writing some detector for, let's say you have some, I don't know, some plant, there is a transporter, and a lot of details are going on that transporter. And you are writing some computer program that detects whether detail on the transporter is good or whether it's bad. So you are saying true, this detail is good, or you are saying false, this detail is bad, so throw it away. How do you think which situation is now more harmful? Is it more harmful to detect good detail as bad or bad detail as good? So which one will cost?
Probably.
Yes, please.
Probably the bad detail is good will cost more.
Yes, absolutely correct. So detecting bad detail is good is now much more harmful than detecting good detail as bad. Why? Because in the case detecting good detail as bad, we just throw away good detail. Okay, that's no good, but okay. In case if you are detecting bad detail as good, you will put it into some car, for example, or into some machinery, and then the whole machinery will break, and you will get much more troubles with that, with the whole machinery broken. So it's the other way around. So as you see, so depending on the situation, you can consider that false negatives or false positives, they have different weight, and you might think that some cases it's okay to make some false positive, in other cases you might think it's okay to make some false negatives. But in any case, it needs you to know the situation and the problem you are considering. You can just put everything into computer and forget about it. It's not the way it works. It's just a pair of hands for you. It's not a substitution for your thinking. So computer won't think for you. So you should do that. Some more characteristics that people were trying to come up with to make that sort of problem more, I don't know, more easy to deal with. So you probably will see such things like confusion matrix. That's the case of this matrix, but for many classes. I will probably ask you to draw some confusion matrices for methods we'll be learning throughout all these semesters, so we'll be doing some classification, and I will ask you, okay, you're doing that method, please draw a confusion matrix, so we can look at it, just eyeball it, and check whether our method is good, not very good, and so on. You will see some simplest metrics like percent of correctly classified items. It's so-called accuracy. But you should be very careful with that parameters, because all these things, they don't carry all the whole information about your problem. So it may it may lose some nuances that you want to know about about the problem you are studying. Precision and recall. Once again, good matters for binary classification. It basically collects that 4 numbers into 2 numbers, but still 2 numbers. You can squeeze it more into 1 number. Moreover, you should be very careful about these characteristics. You will see them here and there, so people are often talking about precision, recall, so on. So, so I want you to know what are they. So basically, as you see, if we have a binary classifier, we sometimes call, when it returns true, we say that it has chosen some item. If it returns false, we say that it didn't choose it. So among that items it has chosen, among the data points, of course there will be some true positives, so the ones that we wanted to choose, but there will be some false positives. Well, real world, what can we do? Of course there will be some. And the percent of the correctly chosen items with respect to all chosen items of this model will give us the precision. So basically what it tells you, so I have some model and it tells me some, I don't know, some true or false. Let's say I'm putting some photo into that model. It tells me whether there is a cat in that photo. So my true is there is a cat. So I call this the chosen item. If it tells me true on some photo, precision will tell me what is the probability, if I take that photo and I look at it, that there will really be a cat. As you might guess, of course, there are some false positives, so there is always some non-zero probability that I will look at the photo and there is no cat. It just so happened that the model missed this thing, so it messed up. And there will be some probability I'll look at it and I see a cat. So that is my precision. What is recall? Recall is the number of correct selected features among all correct features. Here is the case. So you are dealing with the same model that checks you for the cat in the photo. You are putting a bunch of photos in there, let's say 100. And you know that there is 50 photos with the cat and 50 photos without any cats. So you are putting 100 into them. And you are basically expecting, in the case of a perfect model, that it will correctly detect all 50 photos with cats. But it's real world. It detects you, for example, 48. And that percent 48 by 50, that will be your recall. These characteristics are very often used, but you should not be deceived with their simplicity and with the fact that they are often used. They are still tricky. You can't measure the quality of your model basing only on one of these parameters. It's not the way it works, so you can't do that. Why? Let's think about the model that always returns true. Always. I put some photo into it. I wanted to detect a cat in that photo. It says me for any photo there is a cat. Independently, what is on that photo? Maybe it's blank. It still will say me there is a cat. Is this model good? Probably not. It doesn't do any useful work. But what will be recall of this model? Who can tell me?
1?
Yes, correctly. That will be perfect 1. Because if I feed it any photo with a cat, it will classify it as the cat. Besides it classifies it as cats, I don't know, some chairs and desks, but it classifies cats as cats, so recall will be perfect. So if you are basing on recall, you can get into trouble if you get this bad model. Okay, maybe precision is better, but let's look the other way around. So for example, suppose that I'm taking this model that classifies me photos into cat, not cat, and putting a bunch of photos into that model. This model checks me all the photos and returns me true only for one of them, that it's the most sure in. So this model is really sure that that photo contains a cat. It tells me true, and all the rest photos it just tells me false and so. What will be precision of this model?
Probably also 1.
Yes. If it guesses correctly with that photo, if there is really a cat, it will be perfectly 1, because it only once told me true, and if that was a real true, it's 1 by 1, so it's 1. It's a perfect precision. But once again, the model is perfect garbage. You can't use it anywhere. So here is the problem. So you can't use just one of these parameters, so you should be very careful when estimating your model. There are many different, let's say, methods to estimate models that were developed for multi-class classification. Here is so-called F-score. You will probably use it at some point when we'll be getting in all that models of classical machine learning. We'll be using sklearn, and there are already functions for calculating that, and I think you'll be seeing that F measure. So here is the function. It basically takes precision and recall and tries to squeeze them into one number so that we can get some idea about the quality of the model. But as I always tell, there is no perfect way to squeeze the numbers into one, so there always can be some cases when it doesn't play really well. Here is just an example of multi-class classification, so very well-known data set, so-called MNIST. It's just handwritten numbers, and maybe we'll be doing some sort of recognition. We'll see that. Here is the example of generating all the parameters for classification. So I have trained some sort of model, and here are results for different classes. So you see 10 classes here, and you see precision, recall, F1 score for that classes. Support, it's basically like in mathematics. You know what is the support of a function, yeah? So it's set where it's in some sense is defined. So in this case, support means the number of features that belong to that class. So I can tell that class 0 had 38 images connected with it, and class 1 had 43 images, and so on. So just number of images in this case. There are few variations of F-scores. You can probably tune that somewhere in sklearn. I didn't check, being honest. It's like called macro, weighted, and micro. But I don't want to lose some time on that. So probably when we get to our models, you will get acquainted with all that things. Here is an example of confusion matrix. So that's the thing I will often ask you to generate when we'll be dealing with our models. And as you see right now, this one model was quite good enough for the missed data set. So it's almost diagonal. So almost every prediction was correct, and everything is really fine. Of course, you see some numbers off the diagonal, and all these off diagonal values, they tell you that something went wrong, and in that case our model didn't work quite well, but these numbers are quite small, so that's pretty okay. In many cases you'll be able, looking at this matrix, to say that model works well with some classes, but it confuses some different classes. So it may have some 2 classes and it confuses them, like 7 and 1, for example, numbers or something like that. So confusion matrix is really good for getting all the ideas. Separate methods to estimate regression, but I'll probably tell more about it in the lecture on the regression. So I'll show you how to calculate so-called R-squared. And this is the percent of so-called explained variance. If you don't know what it is, don't worry, we'll get to that, and I'll show you all that things, how they work and what do they do.
Could we take a break? Lecture has been going for quite some time.
Okay, maybe if you want, but just a few things left, so I don't know.
5 minutes.
Okay, if you want, let's take 5 minutes, and then I will finish with. Okay. So the next part is choosing among models. So there may be a case when you are solving the problem, and you have different ideas. So you can solve that with this model, with that model, or with some different model. Of course, you want to get the best one. Or you may even have one model, but you have some hyperparameters in that model. So you are setting, I don't know, like some number of clusters in clusterization problem, or some sort of level of regularization if you are doing some regularized linear regression, or so on and so forth. So there are basically some numbers that you are putting into your model, and these numbers you are putting before the training starts. So before the training starts, you are setting that I want this value to be 1, that value to be 10.5, and so on and so forth. And of course, with these parameters, you are in some sense getting a little bit different models. So they are tuned with that parameters, so one model becomes number of different. And you want to search the best one. You can do that search quite different means. You can just generate some number of models with different hyperparameters. You can do so-called a grid search. So when you are taking your hyperparameter and you are changing it with just some delta, and you are testing every model you get to get some idea how good is it, and so on. in this case, once again reiterating the question I had before during this lecture, here is the case when you may want to split your data set into 3 parts. The training set, usually approximately 60% of your data. Of course, all these numbers are approximate, so by no means you are obligated to use them. It depends on the problem, depends on what you do. It just happens, so they are plus or minus in this range for the problems I have seen. But maybe it can be quite different than that. It's pretty okay. So usually it's 60% of data. You are using that to train your model. So you took a model, you set hyperparameters into that, and now you are training it with your training set. After you have trained it, you perform validation. So you validate your model with 20% of data you have. And you do that with each model you have to check. It may be one model with different hyperparameters. That okay. It may be a few very different models. You want to check, for example, how good support vector machine performs, how good decision tree performs, and how good some neural network performs. And you want to compare them all. And you are performing all that things. Basing on the information you get from validation set. So basically what you did, you trained your model, you need some data, you put it into model, you train it. Okay. You validate it with your validation set, so you get some general idea about the quality of this model. Now you have a number of models, you have validated each of them, so you have some number that tells you how good is this model, and you take the best one. And then you run it on one more on so-called test set, the last 20% of your data, you run that winner, and you check how good is it. So you check its quality. So this is the case. How do you think, why do we split this test set? So why do we do that? Why don't we just take results from validation set and tell, well, that is the best model, and here is its quality? Why do we need one more check for quality? Yes, please.
Probably. Okay.
If you have 20% result of our model, but if this model will show normal result in validation set, and we can understand that this model can not understand how it's translated. Предсказать.
Predict it.
Predict.
Predict all of images or validation set. It's one more check our model.
Well, the problem is basically, I don't want you to focus on the exact numbers like 20%, 60%, it's not like that. I want you to think about such a thing. So what I have is the number of different models. So I have a number of different models. So model 1, model 2, model 3, and so on. So here is what I'm basically checking. So I have all these models. Now I have my training set. So I use my training set to train each of these models. I have some trained models. Now I use my validation set to estimate how good is the trained model. And I get some numbers. I don't know, let's suppose that you are measuring something in percents, like 100% is perfect model and 0% it's total garbage. And you have some numbers, some, I don't know, some 80%, 75%, 99%, 11%. So these are trained models. Okay, so 1 prime, 2 prime, 3 prime, 4 prime. How did I get these models? You can think that these are quite different models. Or you can think that I use some hyperparameter that I basically set into the same model, but it's hyperparameter. It's set before I start training. And in scale, let's say it's some sort of hyperparameter, let's call it h. And each of them has its own value of this hyperparameter. Say 0.1, 0.2, 0.3, 0.4. And at the first glance you might think, okay, I did a lot of work, so I have created all these models. I have trained them all. I have validated them all. I have this data. I can exactly tell you that this is the winner. Yeah, so 99%, it's really good, so everyone else are not so good. So this is my winner. But I take it as a winner, so I take this model, I say, yeah, model number 3, I will work with that. But I don't tell its quality is 99%. I use the last one, the test set, to measure its quality once again. And I'll get some different number. Maybe, I don't know, maybe 83 or something even worse than some other model. And here is basically the question, why did I do this last step? So why couldn't I just stay with this number? I wanted to test it once again. So what can get wrong in this scheme? How do you think?
It's like the whole training process is parameterized not only with training set but with validation set, and technically it affects the outcome, like the final model we have.
In some sense, you can think, yeah. So when I'm doing training, what I'm doing, I'm basically searching for some internal parameters of this model. So we recall the start of this lecture, yeah. So I was drawing for you all these sort of models. It's inside. There are some parameters. I'm tuning these parameters to get the best result on the training set. So that's the best I can get when tuning all that parameters. Then I was checking across validation sets to get the idea how good did it generalize. So that was okay. Now think about this parameter, this hyperparameter h, as one of the parameters of training. It's like some sort of extension of our training. I can get into the same trouble with choosing this parameter h, because I'm iterating through this h and I'm choosing the best number here. So now the validation set is, in some sense, it's spoiled, because I have iterated through some parameter to find the best result for this set.
It's the training set for this iteration process.
So for this iteration process, it's like some sort of, it works like training set for this iteration process. So I get into the same problem I had at the beginning with my training and my validation sets. So I was training on some set, but testing on the training set was a very bad idea, because I was checking that my model predicts its own predictions. It was no good. And iterating through this hyperparameter, I get into the same kind of trouble. I am validating on some validation set, and I'm choosing the best one basing on that validation set. But to get the true result, the true idea how good is it, I need to check once again against the set it hasn't seen, it wasn't validated, parameter was not chosen basing on that set. So it must be something quite different, something separate. And just taking this separate set, I can get some general idea how good is my model. Basically, you may find some different schemes of checking all the models and finding the best one and so on. But what I want you just to remember, so whatever you do, whatever procedure you do, you will train your models, you will validate them, find the best ones, and maybe you do something else, find once again something, and so on and so on and so on. At the end of the day, when you get your model and you say, this is the one I want to put into production, this is the model I will put in, I don't know, some server, and I will make some money from it. So I don't know how, create some service. Before you do that, you should perform a final step, testing it against data that wasn't employed in any of the previous steps. So all previous steps, you have done everything you could, and you test it at the end of the day, you test it against some data you didn't use before. And only that will give you some more or less trustworthy result that you can use later when you are characterizing your achievement. So when you are saying my model is 99% good or 85% good or whatever. So that should be based on some independent check. Okay. And basically, yes, please.
Will cross-testing work like also for this purpose good or not? Like just changing, dividing different like.
You mean making cross-validation in the second step?
Yes, cross-validation, yes. For those hyperparameters.
Probably yes. Why I say probably? Well, because if you do two cross-validations in a row, that will take maybe not reasonable amount of time. So one of the minuses of the cross-validation, as you have seen, you are retraining your model every time. And some models, they may take a considerable amount of time to train. For example, some large neural networks can be trained for, I don't know, a week or even a month. And you can't afford even training it twice or thrice. So yes, I think technically that should work, but in practice I'm a little bit doubtful that you will have enough computational power to do that. But that depends on the model. So maybe for some simple models you can put that into practice and that will work. So at least as it looks for me.
Okay, understood.
Okay, now the last part of today's lecture. Before we move to some concrete methods of machine learning and so on, let's check the last thing. What do you do if your method does not work? So, okay, so you are having some problem, you are trying to solve it with machine learning methods, you found a model, you do everything and something goes wrong. So you just get bad results on your validation and you see that your model somehow performs poorly. So what can be the reasons behind all these troubles, and what can you do in case you see this in practice? So first of all, the quality of the data set. Well, there are basically two big branches of troubles you can get into. Troubles with data set and troubles with the model itself. So a few words about the data set. I told you, so good quality data set, it's, I don't know, maybe 80% of your success. So you need a good data set. So that's what you basically need. Your data set may have some insufficient quantity of training data. Depending on the model, you may need more or less data. So that's basically depends. I will tell you just a moment later that what are so-called overfit and underfit, and that depends on the amount of data you have. So in some cases you can solve the problem by just getting more data or something like that. Of course, the simpler model you have, the less amount of data is enough to train your model. If your model is very complicated, it will need a large amount of data. And here is some sort of interplay. Of course, you can't always get the sufficient amount of data, and that's the problem. It means that maybe you should consider or simpler models or do something like that. In some cases, your problem is very complicated and you can't afford to make your model simpler. So you need somehow to get more data. So that may be the case. So sometimes that basically depends on the problem you are solving, and you should estimate how complicated is your problem, how complicated should your model be to solve that problem, because there is some threshold. You can't fit parabola with straight line, yeah, so you need some more or less complicated model. And when you are dealing with that model, basing on how complicated is the model, you should estimate how much data do you need. So do you need a large amount of data or just a little bit? Yes?
There could also be complicated models that require less data than the simpler ones. And I literally experienced it when I was working on my bachelor's thesis. But they have a lot of handcrafted features and various mathematical procedures, and the whole process is a little bit hard to understand. But it turns out that it requires far less data than more straightforward and classic approaches, simpler models.
Some sort of regularization employed, or
they have a hybrid, like neural network plus lots of digital signal processing and handcrafted features in the latent space, and it turns out to be really good.
Yeah, I understand. Yeah, well, basically, complicatedness of model, in my understanding, is basically the number of internal parameters that you turn, and how free are these parameters. So yeah, if you are doing handcrafted features, you are basically cutting away the part of the neural network that was creating that features for you.
Yeah.
So you are throwing it away. So you are basically throwing away a huge amount of parameters. So you are making your model, in some sense, more simple, because it has some smaller number of parameters. Yeah, but it's a really nice take that in some cases you can get away by creating some handcrafted features basing on your knowledge of the subject. So you know what are you dealing with, and you can get the idea. So if I calculate that thing and that thing, for example, some kinetic energy, some pressures, temperature, whatever, they will be some meaningful parameters that can be put later into the neural network. Okay. The next problem with data can be so-called non-representative training data. So if what are we trying to do? We are trying to make our model to generalize properly. So we want our data to be representative. So we don't want some bias in this model. There's a really famous example of sampling bias. It's happened in 1936 during presidential election in the United States when Landon against Roosevelt, and a large poll was performed, so sending some mail and calling by phones to something like 10 million people. It's a really huge amount. They got 2 and 4 million answers and predicted with high confidence that Landon will get 57% of the votes. Of course, you don't know about Lyndon winning, you know about Roosevelt winning with 62% of the votes. And the problem was that the data was biased. So first of all, they were sending mails, and they were using telephone directories to send these mails. And the problem is that all these people that were having phone at that time, they were on average wealthier than people who didn't have phone. So they were missing some part of the voters, and they even didn't get the idea that they are missing. So they were basically getting wrong data. Of course, on that data, they performed some statistics, so on, they did everything correct, but the data was spoiled. So it wasn't representative. So that's why if you are getting some, I don't know, you're doing some poll and so on, you're getting some data, you are trying to get information about all possible kinds of people that live in the country, because if you miss someone, you will get some bad data and your predictions will be wrong. Okay, and of course, just poor quality data, there's nothing to say about. You need good quality data, otherwise everything is bad. And the last thing, bias and variance problem. So these are two problems with the models you can get. First of all, I wanted to show this small picture. It shows you what are basically bias and variance. So the best model we want to get, it's low bias, low variance. So everything we should get to the target. That's good. With low variance, we can get some sort of bias. We should somewhere aside, but variance is low. And you see two models with high variance. How it looks like in practice. When I was telling you about all this sort of function thing, yeah, so we were our training is some sort of searching the function and so on and so forth in the hypothesis set. You see that the difference we get between the perfect function and the function from our training set we get to after we trained. So hypothesis set are all possible functions. Learnable functions, I call that the subset of functions that we can get when we are training on our data set. So that depends on the data set. And when we put the data set into machine, we perform training, it chooses one point from it. This is the function h, and it tells you here is the trained function, here is the result. This function differs somehow from the perfect function. That is biased. But basing on the data set, I told you when I change something in the data set, I can get a little bit different function, a little bit different h. So depending on the data set, I can get different points from these learnable functions. And the size of this set is basically the variance, so how scattered they are. This is the problem with the data set. You change something in the data set, you get something a little bit different. And this is the problem I told you when we were talking about the robustness. So I want my functions to be not so scattered around. And how this looks in practice, what it gives us. Here is some original data. You see points blue and red. Blue points training set, red points validation set. Here is desired result. So this is the perfect function. These points were basically generated from it. So that's what I want my algorithm to retrieve. Now, what happens when I change the flexibility of my algorithm, the number of parameters inside? When there is too little parameters, I get into so-called high bias model, or it's often called underfit. So most often you will hear the word underfit, but it's so-called high bias model. What it means, the set of your trainable functions squeezes to some small almost point. But if your model is so stiff, it's really unlikely that you'll be able to get close to your perfect function. So you'll get big difference, big bias. And you see this bias is represented in the way that you can't fit a parabola with a straight line. It just doesn't work that way. Your model is too stiff. If I will put into my model too many free parameters, you will see what you see on the right slide. This is a high variance model. It overfits the data. You can see that it perfectly passes through each blue point. So any error on the train set is almost zero or perfectly zero. So it looks like perfect. But it has some huge error on the validation set. So here is the first reason for you to do training and validation. You can get the idea how bad things are if you don't do validation. Yeah, it's a simple two-dimensional case, but if you get into 100 or 1000 dimensional things, you can do that just looking at the picture. So you need something to get you some numbers. And you see here that red points are quite off the line. So if you measure the difference, it will be very large. But it perfectly goes through train set. And here is the case of the overfit or high variance model. What it means, so you have a very large set of your learnable functions. There are many functions to choose from, but small changes in your data set may make your function to wander around, and probably due to that overwhelming freeness of that function, you will get something wrong. In theory, that's called bias variance decomposition. So every method, every error you get in machine learning method can be decomposed into two parts. It's bias squared and variance. There is some statement. I will say it's statement because it can be proven for some machine learning methods, but it's wrong for some other machine learning methods. That tells you that there is, I don't know, some equilibrium between bias and variance that you should get to. So when you are getting smaller bias, you are getting bigger variance. If you are getting smaller variance, you are getting bigger bias. It's true for many models, not for all. There are some exceptions. But for many models, it's true. For some models, it's even provable that it is so. So in many cases, you would like to find that equilibrium point that gets you the best result. So here how it looks in practice. So last few images. This is validation curve schematic. So training score, validation score, and here is the model complexity. So the model complexity, I understand it as the number of that free parameters in the model. So the more parameters you get into it, the more flexible your model gets, and the more basically complicated it is. So when it's low complicated, you can draw with that model some straight lines. When it's more complicated, you can do parabolas. When it's really complicated, you can draw, I don't know, a cat with your model. And as you see, if we are getting into more and more complex models, training score always gets better. Why?
Because we fit more in it, like with more parameters, it separately uses like each input point and fits on it.
Yeah. If you are giving your model more and more parameters, it gets, let's say, more and more memory, and at some points it's capable of remembering all the input points with all the outputs we want to get. So it just remembers and it recalls, I know this input, I will get that output, and so on. But it doesn't do any generalization. How do we test for generalization? With validation. And you see that when I'm getting my model more and more complex, I will get something a bit better in my validation score. At some point, it reaches its maximum, and then it gets down. Because the model becomes overcomplicated, it just starts remembering inputs and giving me the outputs I want on the training set, and it stops generalizing. So what I want, really, my best model, is the model with the best validation score, because it does the generalization correctly, and I want it to generalize. Here is once again the example. you see the number, the degree of the curve. I'm trying to fit through the points, and you see training score and validation score. So training score skyrockets and gets almost to 1, and it's always grows. At some point it will be perfectly 1. Validation score gets up, then gets down. So my model becomes overcomplicated. I can't use it. What about training set size? If I told you that the problem is that my model remembers all the inputs and gives me the outputs I expect on that inputs, what if I make my training set bigger and bigger? So I have some overfitting model. Okay, let's make my data set bigger. So maybe that amount of memory it has now with that all internal parameters will be too small for such a big data set. And that's really true. If you see, when I am increasing the size of the training set, I get my training score down. Of course, I'll get it down because I'm having more data, it's more work to do with that data. But I get my validation score bigger because now model cannot overfit. It is forced by me to generalize that data. It can't just remember all inputs and give me the outputs. It should generalize it somehow. So I force it by increasing my training set. So now just as a recap. So the problems you might have with models: high bias or high variance. High bias is called also underfit. High variance is called overfit. So the first one is caused with the fact that your model is too stiff, too low number of parameters. You need more parameters. So what do you do in case of high bias? What do you see first of all? Your model performs poorly on the training set. So this is the sign that you have underfit or high bias. So you have training set, but your model performs poorly. What do? You're trying to add more features. You're trying to use more sophisticated model. Maybe you need more parameters. You decrease regularization. Maybe you don't know what it is. It's some sort of restricting parameters of the model. So for example, some x can be from minus to plus infinity. You are restricted it from -1 to +1. So we will see that in some of the future lectures. You can just uplift that condition and say, okay, let that x be from minus to plus infinity. I'm good with that. So that's what you can do if you have high bias. High variance, just a bit bigger problem. You see no problem in training set, looks okay. But you see many problems on validation, so you see that validation fails. So that is the sign of high variance model, of so-called overfit. Performing good on training set, performing poor on validation set. What do you use? What do you do if you have such a problem? You can try using fewer features. So the number of features is often connected to the number of parameters inside the model, so you can decrease the number. You can use a simpler model. Your model is too flexible. It's too flexible. It's bad. You are trying to make it a little bit stiffer. You can use more training samples. So you can increase the size of your data set and to force your model into generalizing by not giving it the ability to remember every point with the result you want to get. And you can increase regularization. So you are just restricting not the number of parameters, but parameters themselves by telling, I don't want this x to be from minus to plus infinity, let it be from 0 to 1. And that's basically everything. So this last part is about what I should tell you in the future lectures, but I think you can basically see that on our page in the GitHub, on the GitHub server. So I invite you to check that page. All lectures are presented already there. So you can check them. You can even check them, the problems I will propose you for our some sort of terms, first and second, so you can find them there as well. And you can even find their video lectures in Ukrainian from 2020. I didn't change anything drastically in the course, so they are perfectly aligned with the curriculum we have this year. So you can, if you want, you can reiterate once more with that lectures. Okay, so basically I think that everything I wanted to tell you. Maybe you have some statements, questions, whatever. I'm ready to answer or just to listen. Any comments?
Just how homework will how will homework? So is code on GitHub? There will be tasks and
there are workbooks on the GitHub. You can use them to make some problems, but basically I don't basically check if you do them or not. But I'm always open to answer the question if you have any questions with that workbooks. So if you feel that you need some practice, please do that. Check out for that workbooks. There are a number of problems. In some workbooks there's even too many problems. You try solving them, and if you see that you have some troubles, you don't understand some concepts, you don't understand something, you can do something, you can always ask me why it doesn't work or what is meant to be done in that problem, and you check that. So that's basically the workflow.
And in cases when we finish earlier, when the lecture finishes, we can work together on this, we can discuss specific tasks. So that's the practical part. But in principle you can do those at home just for your own practice, like Vitali said.